material. So that's what we're up to. Homework 9 will be the last homework that's on your second exam. So if all goes well, I will be announcing your second exam. The official 2-week announcement will be this Thursday. If you need, for any reason, to know a little bit in advance, then to make any kind of arrangements, then I'm letting you know now. So just going to triple check a few things in the schedule, but I think it should be no problem for me to assign a homework number 9 for end of next week, and then have a few dedicated study days leading up to the second exam to be Thursday the following week. Okay, any quick questions, administrative or logistical, before we start?
But you said 9, homework 9 would not be on there?
Will be on the exam.
Will be, okay.
So that'll be due next week, the exam following week. You have homework 8 due this weekend or something, right? Okay. Any other questions? Okay, so here's what we were talking about last time. I'm basically on this little sideboard here. I'm going to kind of re-sketch out the angular kinematics summary sheet, which I posted for you. This is a kind of useful single page that organizes this topic all together, but it's not going to be available to you on exams. That's just the equation sheets. So I won't lay it out exactly the same, but basically that's what I'm building up on the sideboard. I have the constant angular acceleration equations. Those, of course, only apply if you are speeding up or slowing down in a smooth manner. The equations look exactly the same, just everything replaced by its angular counterpart. Signs go in and signs come out, just like the same as your regular equations. And basically, this is a completely self-contained set of equations which describes everything in terms of angle. So what you're doing, instead of how many meters, is how many radians did you travel? Okay, how much angle did you cover? Instead of talking about how fast you're going in meters per second, it talks about radians per second. So what's your rate at which you cover angle? And when it talks about acceleration, it talks about not meters per second squared, but radians per second squared. So everything's geared towards angle. So we got that all out of the way. And then, of course, this is very akin to one-dimensional motion, because if you're constrained to go along a circle, you can only go one of 2 ways. So we take the plus direction as counterclockwise, clockwise is negative, and we pretty much stick to those conventions exclusively. That's much more of a hard convention for us, rather than when we use the x and y axes, where plus and minus is always in the eye of the beholder, and so WebAssign will generally not have any idea what you want to use, so you have to enter it into in a neutral way. Now what we're doing is we're going to try to tie this kind of island of stuff back into our old stuff. So we're going to try to figure out what's the interconnective tissue between the linear stuff, which we were talking about earlier, and the angular stuff. And we just barely had gotten started with that last time, so let's go back and take a look. This was our equation for how to go back from the angle that you covered to the distance that you've traveled. Okay? So if S is the distance that you've traveled along a circle, this is sometimes commonly called arc length. I'll use S for that. And that's in meters. This is actual physical distance from here to here. And you can relate the distance S to the angle that you've covered, delta theta, with the third ingredient being the radius. Okay? So this is your classic arc length equation. Its most famous subcase is circumference is 2 pi r. That's for when you happen to go not just any fraction, but all the way around the circle. It's really important that you measure the angle in radians, because radians is a way, it's kind of like a fake unit. It's not really a unit at all. We're talking here about ratios. We're talking about ratio of one distance to another. The distance you've traveled along a circle divided by the radius. So here it's really important to use the units of radians, because this is the first time where we don't have our angle trapped inside a sine or cosine or tangent. If all you're going to do is take the sine, cosine, or tangent or whatnot, or maybe those inverse functions, if you just tell your calculator what mode to be in, it'll handle it for you. But this is the first time we've had a raw or naked theta without any trig function applied, so we have to be in the right units now. So we have to be in terms of pi in terms of radians, not degrees. So this is my first equation. And I do also want to point out that there are kind of ghost absolute value signs here. Because anytime you're trying to relate the two, they have very different ways of handling signs. We don't want to have that kind of wash through. For instance, if our angular displacement was clockwise, we'd call it negative, but negative distance has no meaning. So I'm going to copy that over here. That's my first equation. The absolute value signs are never written explicitly, but remember, when you're trying to convert between the two worlds have very different ideas of what sign means, so those can't come through. So if you're trying to connect the two worlds, you're going to have to leave the signs behind. Okay? So what we have is over here, s is the distance in meters, and delta theta is the angle you covered in radians. And the way to get from one to the other is with that extra factor of r. Okay? So let's go ahead and talk about some of the things that happen when you bounce out from angle to distance, when you go from delta theta to s. Let's say we have, I don't know, a spinning platform. So maybe like the top view of a, I don't know, a record player or a carousel, some kind of spinning disc. And we examine 2 points. I guess I'll call this point A and I'll call this point B. And I examine both points as they rotate. So if I look at one time, those points are like this. Later on, point A is like this, and point B is like this. So generally, when you have a spinning object, everything will cover angle together. So A moves like this, when B moves like this. So on the angle side, the angles are the same. But that is not the case on the distance side. Which point travels more distance? B, exactly. So we see that if we have this being fixed, we see that S is proportional to R. So if we take a look at and say that the delta theta term is fixed, we see that the distance traveled is directly proportional to R, which is to say, the further out you are from the center of the circle, the more distance you will travel when you cover a given angle. Okay? So what we can say is that the distance from the center is not equal, therefore the distance traveled is not equal. So this gives us a little bit of an inkling as to why we want to introduce all these angular variables in the first place. If we have a spinning record or a spinning carousel, if we stay in our distance land and talk about meters, we don't notice the commonalities of point A and point B. Point A and point B do not travel the same amount of distance. But if we talk about it in an angle instead, we can say that points A and B travel the same angle. And in fact, it's not only points A and B, it's every point. Every point travels the same angle together. Okay? So that gives us an idea of why it's useful to go over to the angle side instead of just staying in meters land. Okay? So if we progress from here, we can also say that if they cover the same angle in the same time, we can also say that their angular velocities are equal. Right? They cover the same angle in the same time. So remember that the definition of average angular velocity is angle covered per time. In this case, same angle, same time. So at any given moment, at least, we can say that whatever A is doing, B is doing the same. For instance, if we wanted to say that this spins at a constant rate, we might say that they both cover 2 pi of angle in one period. One period is one full circle. So it's nice to be able to say that there's a common property. That's not true again. If you look at the radii, well, they do not cover the same distance in the same time, right? If we were to try to calculate the v, we'd have to do the distance over time. We've talked about this before. It's 2 pi r over t. That we used for orbits. So there it is. We have that pesky r again. So even if the time might be the same, if we suddenly have a r factor in there, then we have the speeds in meters per second are not the same. So you can see why we want to go over to the angle side instead of saying on the meter side. In fact, if we were going to draw our linear velocity vectors over here, they would look like this. This will be the velocity of A. This would be the velocity of B. On a spinning object, the points on the edge travel more meters per second than the points closer in. You see this all the time. If you watch Carousel, all the little kids sit toward the middle, and then the kids that are want to get the maximum thrill out of a carousel, like probably should have graduated to the roller coaster, they always try to get the horses on the edge, right? So if you want the fastest linear speed, you have to go on the edge of an object. However, every point on the object has the same angular rate at any given moment. Even if it's spinning faster or slower, at any given moment you can be guaranteed that the angular speed of any point is the same as any other. All points travel the same angle in the same time. Okay? In fact, the best way to characterize the rotation rate of some extended object is by angular velocity. Because what you are going to say is guaranteed to be true of any point, whether it's closer in to the center or it's further out from the center. Every point sweeps out the same angle in the same time. The SI units we use are radians per second, but there are others. You could talk about degrees per second, or you could talk about revolutions per second, or maybe even revolutions per minute, sometimes known as RPM. Okay? So for instance, a vinyl record spins, and one speed of a vinyl record is 33 RPM. That is basically giving you a non-SI unit of angular speed. Okay? Because you can be guaranteed that every point on the record when it's spinning is spinning with the same, covering the same angle per time. Not the same meters per time, but the same angle per time. So you can see again, if I just take this and divide it by an equal amount of time, the only difference in the relationship will be this extra r. So this doesn't have an r, and this does. And adding it over here, I just have this. So there is how I can convert back and forth between the linear speed and angular speed. If I know what is the radians per second, maybe that's the common radians per second of the entire record, then I specify what r am I doing that at, and then I multiply it in, and that will tell me that particular point, how many meters per second is that traveling. Okay, and so on and so forth. We're finally going to arrive at the acceleration. So now, if something spins, it spins faster or slower than before. Just to spoil the surprise, the correspondence here is angular acceleration and tangential acceleration. So this is radians per second squared, and this is meters per second squared. So just to remind you, tangential acceleration is something we mentioned in passing when we introduced circular motion, and then we threw it away. Well, this is where it makes a comeback. So we have to talk about this. Okay. So let's talk about that a little bit. So as a reminder, in general, when something's going in a circle, the acceleration can, in general, point like that. And we specifically break that acceleration into a centripetal component and a tangential component. That's just to make the problem more digestible, is to think of the action of the acceleration on the velocity in two different pieces. So velocity is composed of speed and direction. Those are the two things that velocity includes. And we basically assign roles here for AC and ATAN. They each get to control one aspect. The centripetal acceleration does not change your speed at all. It just changes your direction. So that's what holds you in a circle. Our homework 6, you spend a lot of time worrying about how much acceleration and force, centripetal force, is needed to go in a circle, and then, okay, what provides that? And we mentioned in passing ATAN, but now we can bring it back. ATAN has nothing to do with making you go in a circle, because it doesn't change your direction, but it does change your speed. So that's most akin to the early part of the course when we were working in one dimension, where we had an acceleration that it was either with or against the motion, but along the same line. So it could make you speed up, slow down, but it couldn't change your motion off of that line. So that's where acentripetal comes in, is it moves you off that line onto another line, which lets you go in a circle. So now, we're coming back to this. And let's go ahead and write down some of these possibilities. So let's say you're going in a circle and speeding up. So let's say something like that. Let's say we're going this way. Okay, so first of all, let's start on the angular side. What is the direction of the angular velocity? Is it clockwise or counterclockwise?
Clockwise.
Clockwise. So we're going clockwise. So the angular velocity is positive. Now, if you want to speed up,
Counterclockwise.
do you think the angular acceleration is the same way or the opposite way? So what would be the angular acceleration? Should it help the angular velocity or go against the other, go the other way? Or to speed up? Same way, right? So anytime you want to speed up, these have to be the same way. Same direction. So they both are counterclockwise. So that's what we'd say on the angular side, right? Let's write in the linear stuff. At that particular moment, my velocity is like that. So how about ATAN? Should ATAN be with or against the velocity? If you want to speed up. With it. So ATAN would be like this. So B and ATAN should be the same direction. They're just two different ways of talking about speeding up. One is in terms of angle and one is in terms of meters, but on the same side, the same idea, whether it's angular or linear, if you want to speed up, the acceleration has to reinforce what the velocity is already doing, okay? Let's do the case of slowing down. So let's say I have something going in a circle in the same way. So the angular velocity is still positive. The direction of motion is still counterclockwise. But now if you want to slow down, what's the angular acceleration direction? It's going to be negative, right? Slowing down. They're in opposite directions. Now the angular acceleration is going to work against the angular velocity. And if I drew in the velocity vector, and I talked about it in terms of meters per second, well, A tan is going to have to be against that. So B and A tan are now opposite. So if I want to talk about the old stuff, it goes like that. Of course, the one case I should not neglect to do is what about if you're going in a circle at a constant speed? So my angular velocity is positive. What's my angular acceleration? 0. I'm going to have constant angular velocity, which means constant speed and also a constant direction, which is positive or counterclockwise in this case. When we're talking about circular motion, that's constant, right? You go in a counterclockwise direction all the time at the same rate, so that's constant velocity in every way. Constant speed, constant radians per second, and also a constant direction, because in this case, we only have two possible directions, counterclockwise and clockwise, and we're always going counterclockwise. And then over here, on the velocity side, what's A tan? How much acceleration do we have tangential to the circle, with or against the velocity? So A tan is 0. We don't need any A tan because we're not trying to change the speed. So we're going to have a constant speed, but here's the thing. If we're talking linear, it's not going to be a constant direction, because on the linear side, as long as you're circulating the same way, you still have to continuously change the direction of your velocity, like this. That's a change. And we learned that that change costs something. That's not A tan's job. A tan's job is to change the speed, but we do still have, okay, notice here that A tan and alpha, they are the corresponding ones. They describe speed change. They're all about going faster, going slower, or maintaining your speed. You can see that when one is 0, the other is 0. These are the corresponding things. But just because you have no angular acceleration and you have no A tan doesn't mean you have no acceleration at all, because even though you're moving in a circle at constant speed, going in a circle is a privilege and not a right. So there is still another kind of acceleration, which is what? Centripetal. Centripetal is always there. Centripetal is what allows you to go in a circle. So in all of these cases, there is still a centripetal acceleration. And even if you want to go in a circle and not speed up, you still need to maintain that circle. So this box here closes out the linear to angular conversions, but there's one thing that's left out in the cold here. We have to remember that there is one quantity which is only in the linear world but not in the angular world. That's centripetal acceleration. That's v squared over r. Now you might ask, why doesn't it have a counterpart in the rotational world? The reason is because the whole premise of the rotational world, the bedrock upon which it rests, is that you are going in a circle. It doesn't ask if you can go in a circle. It says, okay, you are going in a circle, let's describe it. But the linear world, of course, there's lots of different motions that are possible. Some are circles, some aren't. And so we learned that it's a very specific privilege where you get to go in a circle. Okay? So there is no corresponding thing here. This all rests on the assumption that you're already going in a circle, whereas in the linear world, you have to make sure that you get to do that.